So, as part of this course on design for quality manufacturing and assembly, today we will see a method of analyzing the assembly difficulty. When we design, we have to consider the constraints coming from the manufacturing, and we do the DFM, and once these components are fabricated, they need to be assembled to create, let us say, a sub assembly or the final product. So, the degree of difficulty of doing the assembly, either it be manual or it be robotic assembly, needs to be assessed, and based on the indices obtained, one can go ahead with the exercise of redesigning the parts to enable uh, ease of assembly. So, there are many methods to assess the assembly difficulty, uh, methods like the Boothroyd and Dewhurst method, and the method that we are going to discuss in this contact lecture, that is the XPI. XPI stands for Xerox Producibility Index. Xerox, as you know, is one of the pioneering companies which was making the photocopying machine. And if you would have seen a photocopying machine, particularly the interior, you will see that it holds several hundreds of parts assembled together. Thereby, the cost of the product is predominantly determined by the assembly cost along with the part or the component cost. So, the index that can be used for assessing the assembly difficulty could be either the cost, which is essentially in terms of the assembly time. So, most of the methods try to obtain an estimate for the degree of difficulty in terms of the assembly time, which can then be converted into cost based on the labor or based on the automatic assembly line setup cost and the operating cost of the assembly line setup. So, several DFA guidelines can help in redesigning a component to decrease the assembly difficulty, but index which essentially predicts the assembly time is required to objectively evaluate the outcomes of applying the DFA guidelines. So, DFA index could be in terms of time. So, in order to do an assembly analysis, we need to understand the assembly steps. We have to hierarchically put these assembly steps and the associated tools and the attributes, like how is the part being oriented, how is it being grasped, whether some tools are required. So, these attributes needs to be captured so that we can apply any objective way of assessing the assembly and arriving at the assembly difficulty time. So, we generally create what is called as an assembly tree, which puts the assembly operations in hierarchical sequence along with the assembly attributes. Then we can use some lookup tables or charts which can help in assigning the assembly time associated with each of the operation. So, these times are obtained using work time studies on a statistical basis on a number of experiments. The average time required to do a particular type of operation, let us say 2 components needs to be snap fitted or 2 components needs to be assembled using bolt and a nut, or it needs to be riveted. So, these operations are repeated and a statistical measure is obtained as an estimate of the assembly time. So, these numbers are tabulated and these help us in arriving at the estimated assembly time. So, lookup tables are created based on such studies. So, in this uh, lecture we will primarily see one method, which is the XPI analysis, or Xerox producibility index. There are also other methods like Boothroyd and Dewhurst method. So, let us first see how an assembly tree is created. I will take some example assembly and describe how an assembly tree is representative of the sequence of assembly operations that will go into the assembly. The assembly tree is typically an inverted tree where the trunk is the final product and the leaves and branches essentially represent the components or sub assemblies. So, they come together to form and so forth. So, where the final product is the trunk, and these leaves and the branches, they represent various components and assembly operations. So, some of the attributes of assembly that are indicated in the branches of this assembly tree are whether there is a requirement for fixturing, because several operations might need fixtures either to enable the operation to be completed or for the quality of that assembly operation and repeatability of the assembly operation. And when we do assemblies, sub assemblies might have to be reoriented so that they go into the final assembly. Reorientation is an additional step, and which if avoided can reduce the assembly time. And also the degree of difficulty typically depends on insertion direction. A top down approach for insertion is typically the most easily accomplished or the least difficulty operation, but when a component needs to be inserted from a transverse direction or from bottom to top, we can see that there are difficulties associated with visualizing the assembly interface, and as well as the dexterity and the skill that is required to do those operations. So, these attributes affect the degree of difficulty of doing the assembly and thereby the time that is required to do the assembly. So, these are obtained and represented as a assembly tree, and the information is taken into a worksheet which can later be used to compute the assembly time or the DFA index. So, let us take one example, a consumer product. Here you see a coffee mill. So, it constitutes different parts. This is a CAD drawing. So, you can see that there is a motor which is driving the blade which will mill the coffee to make coffee powder. So, this is an household item where you can mill fresh coffee powder from the coffee beans. So, you have the housing, this component, you have the blade and the chamber, which is this component, and the lid. So, this contains the coffee bean inside the chamber and it is milled. The motor is the prime mover which moves the blade and it has some electrical connections like switches and wires. There are some motor mounts to help properly mount the motor, because that is the moving equipment or the component, and it might cause undue vibration if it is not properly mounted. So, let us see how we create an assembly tree for this assembly of this component, and then analyze using Xerox producibility index the assembly difficulty of this component. The complete assembly tree for the coffee mill is shown here. As I have informed earlier, the tree primarily consists of information pertaining to reorientation, if there is any fixturing need, and the insertion direction. Insertion directions could be linear motions or sometimes it might be rotary movement. Like if I have to assemble something where I need a rotary movement, I can also mention the requirement. So, as mentioned earlier, the final product is the trunk over here, and the various sub assemblies and components come as branches meeting together to form the final trunk. So, we can start from the bottom, that means in this inverted tree we can start from the branches and walk towards the tree to understand the assembly sequence. So, if I see two branches, that means these two sub assemblies can be made parallel in two different stations, and then maybe it can be brought in to one station to do the final assembly, or if the entire operation is being done in a single station, then it can be done in sequence. Either first one of the sub assembly or the branches is completed and then the other is taken up, and finally these two sub assemblies are brought in to create the final assembly. So, temporally it can be different, that means in series I can do these operations, or it can go parallel by having two different stations, and one has to see how these time of assembly has to be matched. So, let us start with one of the branches. So, typically we have the part numbers based on some group technology. The company has its own numbering sequence. So, that can be mentioned to describe the part. So, the base part is taken, which is this component that we see in blue, and the switch is attached to the base. So, the base when it is brought in first needs a fixture. So, fixturing is mentioned and it is kept in the fixture in from the top down approach. So, you see the requirement for fixturing and the assembly operation, that is the insertion direction in this chart. Then the switch is brought. So, these operations can be named and one can assign the attributes. If I would like to represent it as a table, I would like to put the assembly sequence or the assembly number, and I would like to write down the corresponding attributes for the assembly. So, once I have put the switch, I will have to do a reorientation so that I can bring in the card and attach it to the switch. The card operation may require, it is not a linear operation, it might need some rotary operation. So, this completes the subassembly associated with the base. Parallelly or in a different station, we can do the assembly of the motor. The motor is taken and the wiring assembly is put, which requires fixtures, and also it might require a rotary or a twisting motion, and the motor mounts are brought. There is a fixturing requirement to assemble the motor mounts and the motor, and I will have to do a reorientation to attach the felt ring. So, I have the motor which has been attached to the motor mounts here, this component that is seen, and finally, this goes into the body, which is marked in yellow, this component. So, I might need some screws to put, and I may need some fixturing. So, once this assembly is done, I can then attach the chamber, which is the blue color, and then the blade, and then the transfer pusher. So, this is the blade and this is the transfer pushers, and once this is done, this part of the sub assembly is completed. So, finally, I bring in this lid. So, the motor mount and the motor assembly is attached to the base using this operation number 12, and finally, I will attach this lid using this operation number 13. I bring the lid in the top down approach, and finally, I do a reorientation to put it in a box, and I might add some assembly instructions or manuals associated with this in the carton, which will contain this component, and I can then send it to the warehouse or for the product to be stored, or it can be shipped to the customer or to the dealer's place. So, this is just as an example to illustrate how the various attributes associated with each assembly operation, particularly the requirement for fixturing, whether there is a reorientation or change in orientation in between the assembly, and the predominant motion pertaining to the assembly operation. Like when I have to do an assembly operation, typically I will have to take a component and insert or place it into another component. So, whether that motion is linear or whether it requires some kind of rotating motion. So, these are captured. So, these attributes are important in computing the assembly difficulty with respect to this method that we are going to discuss based on the Xerox producibility index. So, we create this assembly difficulty index. Just a small historical note. So, developed by the Xerox Corporation in 1985 when they were trying to optimize their assembly operations. The first step we have seen, we have created the assembly tree. The data that we have obtained regarding the attributes of assembly, we will populate it into a data sheet and then use the lookup table to determine the XPI score, which is the degree of difficulty of doing the assembly. So, the XPI data sheet looks like this. So, we annotate the parts or the sub assemblies, and corresponding to each part we would like to describe the assembly operation, the approach direction, whether the part needs to be held when the assembly is being carried out, and what kind of tightening or the operation, fixing operation that needs to be employed, and how many times we are repeating that operation. The score for this operation is obtained based on these attributes and it is tabulated, and the total score is computed by summing up, and this number is then used to either describe directly the assembly difficulty, or it can be converted into assembly time, and that can be used as an indicator for describing the assembly difficulty. So, the approach can be either top, bottom, side or rotated, that is how we bring in the component, and in terms of holding we just describe whether we need to hold or not, and in terms of tightening it could be different types of ways of holding it, that is it could be metallurgical operation like welding or soldering, or we can use some adhesives, or it could be mechanical like pin, nuts, screws or rings and so forth. So, we describe the nature of uh, uh, holding together the components which have been brought in to the assembly. A score sheet is available then to pick up the difficulty or the XPI score. So, in this table you can see that onto the rows we have the assembly approach, like whether we are assembling it from top or from the side, from bias, or we have rotated parts, or we assemble it from the bottom. And we have the next column which tells whether we are holding or not holding, this yes or no. And the tightening operation has been classified as special tools like weld, solder, or the small tools like adhesives, pins, tapes, screws, nuts and so forth. And if we do not have any tool, we can also do assembly without any tools, like we have the snap fit. So, the number 100 essentially means that it has very less assembly difficulty. One can see that if I do not need any tool, that is I do a snap insert, and when I bring a part from top, assemble from top, and I do not need to hold. So, that means in the first row, and if I need to take the last column, that is I do not need any tool, I will get this number 100. So, this is the least difficult assembly operation, and the assembly score actually goes down all the way to 0. Like if I have to do a welding, you can see that it is a very low score, because the difficulty of doing the welding is more as compared to say putting a adhesive or putting a tape. So, the lower the numbers, the higher is the difficulty of doing that operation as described in this table. So, if I have to do some operations from the bottom, you can see that the numbers, score sheets are put as 0, because they are very difficult. So, this table is used once I prepare the XPI data sheet corresponding to each part. When I have captured the attributes, I put this XPI score by pulling up the number from this data sheet, and I complete that table to arrive at the total XPI score. So, for this example we will see how we compute it, and once we have the score, the total XPI score is obtained, and for repeated operations heuristically a number is a score is reduced because if one operation is repeated several times, then the degree of difficulty does not remain the same for each time when I do the operation successfully. That means, if I have to do 4 screws one after the other, the degree of difficulty does not remains the same. So, to account for that, we just negate, this is a heuristic way of negating the score. So, number of times it is repeated, we reduce it and divide it by the number of operations to arrive at an average XPI score for that assembly. So, for this example, component or the product, that is the coffee mill, the XPI score sheet looks like this. On to the left we have the components listed in the order in which we have taken up. Say the first operation is associated with the base, we bring in the switch and then we bring in the card and so forth. So, each of these operation the attributes are listed. So, if we take the base, the number associated with that base operation, so is 0 1, which is what we have given in the assembly tree. If I go back, this is the assembly operation. So, I am writing down the attributes of this. So, here I am bringing it from top to bottom. I need fixturing, and so these attributes are so I bring in the part from top to bottom, and I do not need to fix anything because I have a fixture. I am just going to place that base in that, and I have to repeat the operation only once. So, my assembly score is 100. The same way for the switch, I am bringing from top the direction, and I am just repeating the operation once, and I am not doing any additional operation. So, the score is 100. The card, if you just take the third component, which is put with the operation number 3, if you go back to the sheet which shows the assembly operation, this is the operation. So, it needs a fixture, and it needs a rotating motion. So, this is captured in the table. This is rotated and you need to hold it down, and this is also repeated only once. So, if we see the table, the corresponding number corresponding to that is so you need the parts are rotated and you need to hold hold the component. So, the score is 65. So, that is what has been written here. So, like that, for each of these components the assembly score is tabulated, and depending upon the number of times it is being repeated, it is negated n number of operations, then it is negated, like 10 score is negated. So, let us say if I have to put 2 screws, I will negate 20 from the score. Like here we have 2 screws. So, from 70 I will negate 20, that is it becomes 50. The same way here I have to repeat this operation 2 times. So, from 100 I will negate 2 into 10. So, if you see the 10 into number of times the operation is repeated, that is negated. So, that is what we see in this column, and this column is summed up and divided by the total number of operations. So, the average XPI number comes to around 82. So, if it is 100, actually the score is good, that is the difficulty of assembly is very less, and as the score goes down, the degree of difficulty of assembly is more. So, one can also convert this into time using say some conversions. So, we can do an assembly operation and find the time and benchmark that and use that as the standard time. We compute the assembly difficulty for this method, that is the XPI indicator, and we take these two as the numbers and do a mapping. That means, if there is a change in the assembly score, how far the assembly time can change. So, this is again an extrapolation, and we can use some function to extrapolate this. So, the suggested method is to use an constant k and an exponential function to compare two assembly scores and the and arriving at the assembly time. Let us say this XPI nominal is a benchmark part which has been assembled, and the XPI score corresponding to that part is computed, which is this XPI nominal. Corresponding to that, the measured time, experimentally measured time, statistically measured time is T nominal. Then for a changed design, if XPI is the score, then using this equation one can obtain the estimated assembly time. So, one has to use an appropriate constant k, and it is suggested because this k is a scaling factor which needs to be used to convert the difference in this XPI score to help in estimate the difference between the assembly time. So, the k value is typically chosen as the log 2, that is 0.69. The idea is that the deviation is not more than twice the nominal time, because when I try to extrapolate the XPI score to get the assembly time, if I have let us say the score becomes more than twice the nominal score, then the extrapolation for the time may not be the nonlinearity in the relationship cannot be captured beyond that. So, this basically limits my range of interpolation, so that the new time is within 0.5, that is half the nominal time to twice the nominal time. So, this is just to ensure that the range of estimation is limited to basically half or twice the nominal time. So, one needs to understand that it only helps in understanding the time trends, and it may not exactly determine the assembly time that may be required. So, if we do a redesign, let us say we do a DFA exercise where the current assembly is taken up and we try to propose a new assembly, this tool can be used to estimate or give a trend whether the degree of difficulty will overall degree of difficulty whether it will increase or decrease. So, that kind of a trend can be obtained and may not be used to actually get the realistic assembly time. So, there are other methods like the Boothroyd and Dewhurst method. There are methods proposed by Munro and associate, where sometimes the predictions are better, but this is one of the earliest attempts in understanding the complexity of doing an assembly and how it can be quantified using an assembly difficulty index and can help in doing the design for assembly. Thanks.